September 1944. A young Luftwaffe pilot climbs into his Messerschmitt Bf-109 at an airfield outside Berlin. He's been told the American bombers are coming again. But this time, something's different. His squadron commander's face is pale. The fuel rations are half what they used to be. And then the commander says something that makes his blood run cold. "They're bringing Mustangs all the way to Berlin." The pilot laughs nervously. "That's impossible. No single-engine fighter can fly that far." His commander doesn't laugh back. "Tell that to the 200 pilots we lost last month." 3 hours later, that young pilot would look up at 28,000 feet and see something that shouldn't exist. A formation of sleek, silver American fighters with the range of a bomber and the speed of an interceptor. The last thing he'd hear through his radio would be his wingman screaming in terror as a P-51 Mustang dove out of the sun at 440 miles per hour. This is the story of how one aircraft changed the entire course of World War II. But more specifically, it's the story of how an obscure metallurgist's decision to use a controversial aluminum alloy turned an average fighter into the most feared weapon in the sky. It's a story of innovation born from desperation, of engineering genius meeting the crucible of war, and of how the right material in the right place at the right time can alter history itself. Let's rewind to 1938. The storm clouds of war are gathering over Europe. Hitler has annexed Austria. Czechoslovakia will be next. And in the corridors of power in London, a grim realization is setting in. Britain is woefully unprepared for the air war that's coming. The British government establishes a purchasing commission in the United States. Their mission is simple but urgent. Buy American fighters. Lots of them. The problem? There aren't many to buy. The American aircraft industry in 1938 is still in its infancy compared to Britain's. The best fighter available is the Curtiss P-40 Tomahawk. It's decent, but it's no match for the German Messerschmitt Bf-109. And Curtiss is already running at full capacity. There simply aren't enough P-40s to go around. Sir Henry Self, the man leading the British Purchasing Commission, finds himself in a frustrating position. He needs fighters yesterday, but the only company with capacity is North American Aviation. And they've never built a fighter before. They make trainers, the Harvard trainer to be specific, which the RAF is already using. Good trainers, but trainers nonetheless. In a meeting that would change aviation history, North American's president, James Dutch Kindleberger, makes an audacious proposal. Instead of building P-40s under license, why not design a completely new fighter? A better fighter. And here's the kicker. They can have a prototype ready in 120 days. The British officials look at each other in disbelief. The P-40 took years to develop. The Spitfire took years. The Hurricane took years. And this American is claiming he can design and build a brand new fighter from scratch in 4 months? Self is skeptical, but he's also desperate. On May 4th, 1940, he signs a letter of intent. On May 29th, the order becomes official. 320 aircraft. Unit cost not to exceed $40,000. First production aircraft by January 1941. And one more crucial specification buried in the contract. The airframe must be constructed to save weight wherever possible. That last requirement would prove to be the key to everything. Enter Edgar Schmude, a German-born engineer with Austrian citizenship who immigrated to America in 1925. Schmude had worked for Fokker, one of the legendary aircraft companies of World War I. He understood aerodynamics, he understood structures, and crucially, he understood materials. When Schmude assembled his design team at North American's Inglewood, California facility, he faced an impossible challenge. Create a fighter that could outperform everything else in the sky. Make it fast. Make it maneuverable. Make it long range. And, oh, by the way, do it in 102 days, because that's all the time we have. Most engineers would have played it safe. Copy the P-40's basic layout. Use proven materials. Stick to conventional wisdom. But Schmude wasn't most engineers. He had a radical idea. and it centered on a material that many considered too risky for combat aircraft. Aluminum alloy 24ST, later known as 2024 aluminum. A form of duralumin? Now, aluminum itself wasn't new to aviation. The Germans had pioneered duralumin in World War I. The British used it in the Hurricane. But 24S was different. It was a newer alloy developed by Alcoa in the United States. An aluminum-copper-magnesium alloy with extraordinary properties. It was 15% lighter than steel with comparable strength. It could be easily machined and formed. It had excellent fatigue resistance. And critically for Schmued's purposes, it could be manufactured in large sheets that were perfect for creating smooth, low-drag surfaces. But 24S had a reputation problem. It was considered temperamental. It required precise heat treatment. If not properly handled, it could develop stress corrosion. Some metallurgists warned it was too unreliable for military use. The British had rejected it for some applications. The term forbidden alloy wasn't official, but it circulated in engineering circles. 24S was the material you used when you were willing to take risks. Schmued was willing to take that risk because he understood something that others didn't. The performance advantages weren't just marginal. They were revolutionary. By constructing the entire fuselage from 24S aluminum alloy in a semi-monocoque design, Schmued could create an airframe that was both incredibly strong and remarkably light. This wasn't just about saving a few pounds here and there. This was about fundamentally changing the weight equation of the entire aircraft. Think about it this way. Every pound you save in the airframe is a pound you can add in fuel, or ammunition, or equipment. The weight savings from using 24S instead of conventional materials translated directly into combat capability. More fuel meant longer range. Longer range meant you could escort bombers deeper into enemy territory. Deeper penetration meant you could hit targets that were previously untouchable. But here's where Schmued's genius really shines. He didn't just use 24S for the fuselage. He integrated it into every aspect of the design. The airframe was divided into 5 main sections: forward fuselage, center fuselage, rear fuselage, and 2 wing halves. Each section was constructed separately, fitted with wiring and piping, and then joined together. This modular approach meant faster production. It also meant that damage to one section didn't necessarily compromise the entire aircraft. The 24S alloy was formed into smooth, mathematically lofted curves using conic sections. This wasn't eyeball engineering. This was precision mathematics, creating surfaces with minimal drag. Every rivet was flush. Every joint was faired. The result was an airframe that slipped through the air with far less resistance than its contemporaries. But Schmued had another trick up his sleeve: the wing. Working with the National Advisory Committee for Aeronautics, NACA, Schmued developed a revolutionary wing design based on laminar flow airfoils. The NACA 45-100 series airfoil, to be specific. Conventional wings created turbulent airflow. Turbulent airflow meant drag. Lots of drag. But laminar flow airfoils were designed to keep the air flowing smoothly over the wing surface for as long as possible. Instead of the air breaking up into chaotic eddies right behind the leading edge, it stayed smooth and attached almost all the way to the trailing edge. The difference was measurable and massive. In wind tunnel tests at the University of Washington, Schmued's laminar flow wing produced significantly less drag at high speeds compared to conventional designs. This translated directly into higher top speed and better fuel efficiency. The Mustang could go faster and farther on the same amount of fuel, but there was a catch. Laminar flow wings required incredibly precise manufacturing. The surface had to be almost perfectly smooth. Any imperfection, any rivet head standing proud, any paint run or dent would trip the airflow and destroy the laminar effect. This is where the 24S aluminum alloy proved crucial again. Its excellent formability and machinability allowed North American to create wing skins with the tolerances necessary to maintain laminar flow. In practice, wartime manufacturing and combat damage meant that true laminar flow was rarely achieved over the entire wing. But even partial laminar flow was enough to give the Mustang a significant performance advantage. And pilots reported that the Mustang felt different in the air. Slippery, smooth, like it wanted to go fast. On September 9, 1940, exactly 102 days after the contract was signed, the prototype NA-73X was rolled out of the North American factory. It gleamed under the California sun. Silver aluminum skin stretched taut over the sleek airframe. It looked fast just sitting there. But there was a problem. The Allison V1710 engine that was supposed to power it hadn't arrived yet. Bureaucratic delays, supply chain issues, the usual wartime chaos, so the beautiful prototype sat there, engineless, for another 47 days. Finally, on October 26, 1940, with test pilot Vance Breese at the controls, the NA-73X took to the air for the first time. And immediately, everyone knew they had something special. The aircraft handled beautifully. It was stable but responsive. It had remarkable fuel capacity. The landing gear was sturdy. The cockpit visibility was excellent. By all accounts, it was an outstanding aircraft, but it had one glaring weakness: altitude performance. The Allison V1710 engine was a fine piece of machinery at low altitudes. At sea level, it produced a respectable 1,150 horsepower. But it had a single-stage, single-speed supercharger. Above 15,000 feet, the power dropped off dramatically. And in European combat in 1940, most of the fighting was happening above 20,000 feet. The Spitfires and Messerschmitts were dancing at altitudes where the Mustang wheezed. When the first production Mustang Mk aircraft arrived in Britain in late 1941, the RAF immediately recognized both the aircraft's potential and its limitation. They assigned it to Army Cooperation Command for tactical reconnaissance and ground attack. Flying low and fast, the Mustang was superb. RAF pilots used it for rhubarb raids, skimming over the French countryside at 50 feet, shooting up locomotives and barges and convoys. The Mustang's speed and range made it perfect for these missions. But for high-altitude combat against the Luftwaffe, it simply couldn't compete. The beautiful airframe that Schmood had created, with its revolutionary aluminum construction and laminar flow wings, was being held back by an inadequate engine. It was like putting a lawnmower engine in a Ferrari. And then, in May 1942, everything changed. Ronald Harker was a test pilot for Rolls-Royce. He'd flown everything: Spitfires, Hurricanes, Typhoons. When he got his hands on a Mustang MKI for evaluation, he was impressed by the airframe but disappointed by the high-altitude performance. Flying back to Rolls-Royce's facility at Hucknall, an idea formed in his mind. What if you took that magnificent Mustang airframe and married it to the Merlin 61 engine? The Rolls-Royce Merlin was legendary. It powered the Spitfire and the Hurricane. But the Merlin 61 was something special. It featured a two-stage, two-speed, intercooled supercharger designed by Stanley Hooker. This supercharger could maintain high-power output all the way up to 28,000 feet and beyond. While the Allison V1710 in the Mustang produced 1,150 horsepower at 11,800 feet, the Merlin 61 produced 1,390 horsepower at 23,500 feet. Harker made his pitch to the Rolls-Royce engineers. They loved it. They contacted North American. Schmood flew to England to examine the project. Everyone involved understood they were looking at something potentially game-changing. In October 1942, the first Rolls-Royce Mustang X, powered by a Merlin 65 engine, took to the air at Hucknall. The performance was staggering. Top speed jumped from 390 miles per hour to 440 miles per hour. Service ceiling went from 31,000 feet to 42,000 feet. Rate of climb increased by 50%. Suddenly, the Mustang wasn't just competitive at high altitude. It was superior. Back in the United States, Packard had licensed the Merlin for production as the V-1650. North American wasted no time. In July 1942, even before the Mustang X had flown, they received a contract for 2 XP-51B prototypes powered by the Packard Merlin. The first flew in November 1942. The results were so promising that the Army Air Forces had already placed an order for 400 aircraft back in August, 3 months before the first flight. But even with the Merlin engine solving the altitude problem, the Mustang still faced a critical limitation. Range. Here's the brutal arithmetic of aerial warfare in 1943. A B-17, Flying Fortress, flying from England to targets in Germany, needed fighter escort, or it would be slaughtered by German interceptors. The Luftwaffe had learned to mass their fighters and attack bomber formations in waves. Without escort, bomber losses could reach 25% or higher. That wasn't sustainable. The P-47 Thunderbolt was a great fighter, but its range was limited. It could escort bombers to the German border and then had to turn back. The P-38 Lightning had better range, but it suffered from poor reliability and cold weather issues. What the Army Air Forces desperately needed was a fighter that could escort bombers all the way to Berlin and back. A combat radius of over 800 miles. Most experts thought it was impossible. Single-engine fighters simply couldn't carry that much fuel. But Schmued's lightweight aluminum airframe created possibilities that didn't exist with heavier conventional construction. Remember, every pound saved in structure is a pound available for fuel. And the P-51B had saved a lot of pounds. The standard P-51B had 184 gallons of internal fuel in the wings. That gave it a respectable range, but not enough for deep penetration missions. In July 1943, the Army Air Forces directed all fighter manufacturers to maximize internal fuel capacity. North American's engineers calculated that they could add an 85-gallon fuselage tank behind the pilot without exceeding the aircraft's center of gravity limits. This is where the lightweight construction proved absolutely critical. On a heavier airframe, adding 85 gallons of fuel, which weighs over 500 pounds, would have pushed the center of gravity out of safe limits. But on the Mustang's light 24S aluminum structure, it was possible. Just barely, but possible. With a full fuselage tank, the aircraft became slightly tail-heavy and less maneuverable. But pilots learned to burn off the fuselage fuel first before engaging in combat. But even 269 gallons wasn't enough for Berlin, so they added external drop tanks, 2 75-gallon tanks under the wings. Later, they developed 108-gallon tanks, and in a stroke of innovative desperation, they even created drop tanks made of compressed paper. Paper tanks were lighter than metal. They were cheap. They denied scrap metal to the enemy when dropped, and they worked perfectly well for their intended purpose. With full internal fuel and drop tanks, a P-51D could carry over 450 gallons of fuel. Combined with the efficient Merlin engine and the low-drag airframe, this translated into a combat radius of over 850 miles. Berlin was 600 miles from England. Suddenly, the impossible had become routine. The Mustang could fly to Berlin, fight for 20 minutes over the target, and fly home. No other single-engine fighter in the world could do that, and it was only possible because of Schmued's decision to build the airframe from lightweight aluminum alloy. December 1943, the P-51B Mustang enters service with the 8th Air Force in England. The impact is immediate and devastating to the Luftwaffe. Let me paint you a picture of what it was like to be a Luftwaffe pilot facing Mustangs for the first time. You're flying a Messerschmitt or a Focke-Wulf FW-190. You've been trained to attack American bomber formations during the window when they're unescorted. The P-47s and P-38s have turned back because they're at the limit of their range. For the next hour or two, the bombers are yours. You and your squadron mates form up for a frontal attack. 30 fighters in a wall, closing at a combined speed of 600 miles per hour. The plan is to blast through the formation, guns blazing, then turn and attack from behind. But today, something's different. Your radar operators are reporting fighter contacts at high altitude. That doesn't make sense. The American fighters should have gone home by now. You push your throttle forward and climb, and then you see them. A formation of sleek silver fighters with invasion stripes. Mustangs. Your heart sinks. The Mustangs have several advantages. First, they're at your altitude. The Merlin engine gives them excellent high-altitude performance. Second, they're fast. At 25,000 feet, a P-51D can hit 440 miles per hour. Your BF-109 can match that, but only in a dive. Third, they're everywhere. There are dozens of them. And fourth, and this is the psychological killer, they shouldn't exist. Fighter escorts aren't supposed to be here, 600 miles from England. But here they are anyway. The engagement is brief and brutal. The Mustang pilots have been training for months. They know their aircraft. They trust the 24S aluminum airframe to handle high-G maneuvers. They trust the laminar flow wing to stay attached in violent turns. They trust the Merlin engine to deliver power when needed. And their trust is rewarded. You try to dive away. The Mustang follows. You try to turn. The Mustang turns inside you. You try to climb. The Mustang stays with you. One of your wingmen is hit and trails smoke. Another breaks formation in panic. And all the while, the American bombers continue toward their target, untouched. This scenario played out hundreds of times in early 1944. The Luftwaffe lost pilot after pilot. Experienced aces who had survived years of combat were being shot down by American pilots on their first missions. The kill ratio was devastating. By September 1944, P-51 Mustangs were achieving a 11-to-1 kill ratio against German fighters. The Germans tried everything. They developed the heavily armed and armored FW-190A8 Sturmbach, specifically to attack bomber formations. But loaded down with extra cannons and armor, the Sturmbach was slow and unmaneuverable. Easy prey for Mustangs. They tried mass attacks with overwhelming numbers, but the Mustangs could break up these formations before they reached the bombers. They even resorted to ramming attacks out of desperation. Nothing worked. The Mustang was simply too good. But combat takes a toll on aircraft. And this is where the choice of 24S aluminum alloy had both advantages and disadvantages. The advantage was repairability. Aluminum can be patched relatively easily in field conditions. A damaged wing panel could be replaced. A holed fuselage could be riveted over. Ground crews became expert at keeping battle-damaged Mustangs flying. The disadvantage was vulnerability. Aluminum doesn't stop bullets very well. A single 20mm cannon shell could tear through the Mustang's thin skin and cause catastrophic damage. The engine cooling system was particularly vulnerable. The Merlin was liquid-cooled, which meant it relied on glycol coolant flowing through radiators. One hit to the coolant system, and the engine would overheat in minutes. Pilots learned to nurse damaged Mustangs home, watching the temperature gauge creep toward the red line, praying the engine wouldn't seize. German pilots quickly learned that the Mustang's Achilles heel was its cooling system. If you couldn't outrun it, if you couldn't outturn it, maybe you could get lucky with a single good hit. But getting that hit required surviving long enough to get into firing position. And that was increasingly difficult as the war progressed and more Mustangs filled the sky. By mid-1944, the 8th Air Force was fielding 14 fighter groups. All but one flew Mustangs. On a single mission, several hundred P-51s could be airborne simultaneously, escorting bomber formations to targets across Germany. The Luftwaffe was being overwhelmed by sheer numbers, superior tactics, and better equipment. The definitive version of the Mustang was the P-51D. It featured a bubble canopy that gave the pilot 360-degree visibility. It was armed with 6 50-caliber machine guns, 3 in each wing, with 1,180 rounds of ammunition total. It could carry bombs or rockets on underwing pylons for ground attack missions. And most importantly, it retained all the features that made earlier Mustangs great. The lightweight 24S aluminum airframe, the laminar flow wing, the powerful Merlin engine, The long-range fuel capacity. Production ramped up dramatically. North American's Inglewood plant was churning out Mustangs at an incredible rate. The Dallas plant came online and produced P-51Cs. By the end of the war, over 15,000 Mustangs had been built. They served not just with the Army Air Forces, but with the RAF, the RCAF, the RAAF, and numerous other Allied air forces. The P-51 flew 213,173 combat sorties in World War II. Mustang pilots claimed 4,950 enemy aircraft destroyed in aerial combat. The combat loss rate was 1.2% per sortie. For context, that's remarkably low for a fighter that spent most of its time deep in enemy territory. But raw statistics don't capture the psychological impact. Hermann Göring, commander of the Luftwaffe, famously said, "When I saw Mustangs over Berlin, I knew the jig was up." German fighter ace Günther Röll described the Mustang as the most difficult opponent I faced. Another ace, Adolf Galland, called it the best fighter of the war. These weren't empty compliments from defeated enemies. They were honest assessments from highly experienced combat pilots who had flown against every Allied fighter type. And what they were really acknowledging was that the combination of innovative materials, brilliant design, and powerful engines had created something that simply couldn't be beaten by their conventional aircraft. Let's zoom out and consider the broader implications of Schmud's decision to use 24S aluminum alloy. The Pacific theater in World War II was defined by distance. Island-hopping campaigns required aircraft that could fly long distances over open ocean. The P-51 proved equally valuable there. The very long-range variant, the P-51H, was designed specifically for the Pacific and could fly even further than the D model. Though the war ended before it saw significant combat, the H model represented the ultimate expression of Schmud's design philosophy: lighter, faster, longer-ranged. After World War II, the Mustang continued to serve. It saw extensive combat in Korea, where it excelled in the ground attack role. Jet fighters like the F-86 Sabre took over air superiority missions, but the Mustang remained valuable for close air support. It was cheaper to operate than jets, could carry a heavy weapons load, and had better loiter time over the battlefield. Some air forces operated Mustangs into the 1980s. The Dominican Republic didn't retire its last Mustangs until 1984. Think about that. An aircraft designed in 1940 was still militarily relevant 44 years later. That's a testament to how fundamentally sound the design was, but perhaps the most lasting legacy is in materials science. The success of the P-51 demonstrated that advanced aluminum alloys could be used successfully in high-performance aircraft. After the war, 2024 aluminum and its derivatives became standard in aircraft construction. Modern airliners, fighters, and general aviation aircraft all use aluminum alloys descended from the 24S that Schmud chose for the Mustang. The Boeing 737, aluminum alloy airframe. The F-16 Fighting Falcon, significant aluminum alloy structure. Even modern composite aircraft like the Boeing 787 still use aluminum alloys for many components. The lessons learned from the Mustang's construction influenced decades of aircraft design. There's a deeper lesson here about innovation and risk-taking. Schmud could have played it safe. He could have used proven, conventional materials. He could have copied existing designs, but he didn't. He took a calculated risk on a controversial material because he understood that extraordinary results require extraordinary measures. This is a pattern you see throughout technological history. The people who change everything are rarely the ones playing it safe. They're the ones willing to bet on unproven technologies, to challenge conventional wisdom, to ask, what if, when everyone else is saying, that's impossible. But here's the crucial distinction. Schmud's risk-taking wasn't reckless. It was informed. He understood the properties of 24S aluminum. He knew its strengths and limitations. He designed around its weaknesses, and exploited its advantages. He tested extensively. He refined constantly. The NA-73X prototype wasn't just thrown together. It was carefully engineered using the best scientific understanding of the time. This combination of bold vision and rigorous engineering is what separates successful innovation from expensive failure. And it's a lesson that remains relevant today, whether you're designing aircraft or developing software or building businesses. Let me take you back to that young Luftwaffe pilot we met at the beginning. He survived the war. In interviews years later, he was asked what it was like to face Mustangs. His answer is telling. It wasn't just that they were fast or maneuverable or well-armed, he said. It was that they were always there. Every mission, deeper and deeper into Germany. We knew that the Americans could build anything they wanted. But we thought distance would protect us. We thought our fighters could at least dominate over our own territory. When the Mustangs appeared over Berlin, it broke something in us. It was proof that American industry and American engineering had solved a problem we thought was unsolvable. And if they could do that, what else could they do? It became obvious we were going to lose. That's the real impact of the P-51 Mustang. Yes, it shot down thousands of German aircraft. Yes, it enabled the strategic bombing campaign. Yes, it was a superb fighting machine. But more than that, it was a symbol. A symbol that innovative thinking and superior technology could overcome any obstacle. That what seemed impossible could become routine with the right combination of materials, design, and determination. And it all started with one metallurgist's decision to use a controversial aluminum alloy that others were afraid to trust. P-51 Mustang is arguably the most important fighter aircraft of World War II. Not because it was the fastest, though it was among the fastest. Not because it was the most heavily armed, though 650 caliber machine guns was formidable. Not because it was the most maneuverable, though it handled beautifully. But because it had the range. And that range was only possible because of the lightweight aluminum construction. Every decision Schmood made cascaded into the final capability of the aircraft. The choice of 24S aluminum saved weight. The saved weight allowed more fuel. More fuel enabled longer range. Longer range meant escort to Berlin. Escort to Berlin meant the bombers could survive. Surviving bombers meant German industry was destroyed. Destroyed industry meant Germany lost the war. That's not hyperbole. Historians broadly agree that the strategic bombing campaign against Germany significantly shortened the war. And the strategic bombing campaign was only sustainable once long-range fighter escort became available. And long-range fighter escort meant the P-51 Mustang. You can draw a direct line from Schmood's material choice to the end of World War II in Europe. Today, several hundred P-51 Mustangs remain airworthy. They're prized by warbird collectors and regularly appear at air shows. The sound of a Merlin engine is instantly recognizable to aviation enthusiasts. That deep, throaty roar is the sound of 1,190 horsepower driving a four-bladed propeller through the air at 440 miles per hour. When a Mustang performs a high-speed pass at an air show, the crowd always reacts. Because even 80 years after its first flight, the P-51 still looks fast. The sleek lines, the purposeful stance, the business-like functionality. It doesn't look like a museum piece. It looks like a predator. And that's Schmoed's lasting achievement. He created an aircraft that was not only effective but beautiful. Form followed function, and the function produced forms of elegant simplicity. The Mustang looks the way it does because that's what the physics demanded. And the physics demanded aluminum alloy construction to achieve the weight savings necessary for the performance requirements. So what can we learn from the P-51 Mustang story? What lessons does it hold for us today? First, materials matter. The right material in the right application can enable capabilities that would otherwise be impossible. Whether you're building aircraft or bridges or computer chips or anything else, understanding the properties of your materials is fundamental. Second, calculated risk-taking drives innovation. Schmoed could have used conventional materials, But he didn't. He understood that achieving superior results required superior methods. But his risk-taking was informed by deep technical knowledge, not blind faith. Third, weight is always the enemy in aerospace. Every pound saved creates opportunities. This principle remains true today. Modern aircraft designers obsess over weight savings just as Schmood did in 1940. Carbon fiber composites, titanium alloys, advanced aluminum alloys, these are all modern expressions of the same principle. Lighter is better. Fourth, integration matters more than individual components. The P-51 wasn't successful because of just the aluminum alloy, or just the laminar flow wing, or just the Merlin engine. It was successful because all these elements were integrated into a coherent design that amplified their individual strengths. Fifth, production engineering is as important as design engineering. It doesn't matter how brilliant your design is if you can't build it in quantity. North American designed the Mustang from the start for mass production. The modular construction, the use of standard materials and processes, the attention to manufacturability, these enabled rapid production scaling. And finally, performance speaks louder than politics. The Mustang was designed for the British, based on British specifications, using a British engine. But it became the most important American fighter of the war because it worked. Institutional resistance, not invented here syndrome, bureaucratic inertia, all of that melted away in the face of overwhelming combat effectiveness. There's a wonderful moment in 1944 that captures the essence of the P-51's achievement. General Jimmy Doolittle, commander of the 8th Air Force, issued a directive to his fighter pilots. Previously, they had been instructed to stay close to the bomber formations, providing tight escort. Doolittle changed that. He told the fighter pilots to go hunting, find the Luftwaffe, and destroy them wherever they were. On the ground, in the air, it didn't matter. The goal was complete air superiority. This directive was only possible because of the Mustang's capabilities. The P-47s and P-38s didn't have the range to go hunting deep in Germany and still protect the bombers. But the Mustangs did. They could escort the bombers, then break off to attack German airfields, then return to pick up the bombers on the way home. The lightweight aluminum airframe and the long-range fuel capacity made this tactical flexibility possible. The results were catastrophic for the Luftwaffe. By mid-1944, German fighter pilot training was down to just a few dozen hours. Experienced pilots were being killed faster than they could be replaced. Fuel shortages limited training even further. When these inexperienced pilots encountered veteran Mustang pilots flying superior aircraft, the outcome was predictable. In June 1944, the D-Day invasion of Normandy took place under near-total Allied air superiority. The Luftwaffe was barely able to contest the invasion. Pilots who survived the war reported feeling helpless. They would take off knowing that Mustangs were probably waiting for them somewhere. Every mission felt like a suicide mission. This wasn't inevitable. If the Mustang hadn't existed, if long-range escort hadn't been possible, the strategic bombing campaign would have failed. Bomber losses would have been unsustainable. D-Day might have been delayed or even cancelled. The war would have lasted longer. Hundreds of thousands more people would have died. The world would be different, all because of material science. All because one engineer chose aluminum alloy 24ST instead of playing it safe. Let me leave you with one final thought. In warfare, victory often goes not to the biggest or strongest, but to the most adaptable and innovative. The P-51 Mustang embodied innovation at every level. Innovative materials, innovative aerodynamics, innovative engine integration, innovative tactics enabled by innovative capabilities. The Luftwaffe at the start of World War II was arguably the best air force in the world. Experienced pilots, modern aircraft, proven tactics, but they became locked into their methods. They refined and improved, but they didn't revolutionize. The Messerschmitt Bf-109G was better than the Bf-109E, but it was still fundamentally the same aircraft. Incremental improvement. The Allies, and particularly the Americans, took a different approach. They weren't constrained by existing designs or conventional wisdom. They were willing to try radical solutions to difficult problems. The P-51 Mustang was one of those radical solutions, and it worked. In the end, the forbidden alloy wasn't forbidden at all. It was the key to everything. Edgar Schmidt's willingness to embrace a controversial material, to build his entire design around its unique properties, created an aircraft that changed history. The lightweight aluminum construction enabled the long range. The long range enabled the escort missions. The escort missions enabled the strategic bombing campaign. The bombing campaign helped win the war. One material, one decision, one aircraft. The world changed. The next time you see a P-51 Mustang at an air show, or in a museum, or in a photograph, remember that sleek aluminum skin isn't just metal. It's innovation made manifest. It's proof that the right material in the right design can achieve the impossible. And it's a reminder that sometimes the most important breakthroughs come from being willing to trust in something others call forbidden.